Revision Lecture 02, Digital Logic Basics. In digital logic, we effectively have two discrete levels. These are logical 1, or true or on, and logical 0, which is false or off. So when it comes to representing these logical values, we of course use voltage levels. So depending on what sort of family of logic chips you're using, these voltage levels can vary. And they also vary in two distinct ways. One is the ranges in which these chips drive those logical values, and the range in which these chips read those logical values. So shown in the picture here, I have got various logical families: CMOS, TTL, CMOS, TTL, ETL, and low V, BTL, and GTL logical families. So I've shown in this picture the various ranges in which they drive their logical values out to a chip down the line, and also the ranges in which they read their logical values. So when it comes to picking a logical family, you effectively need to stick to it, because a lot of these families do not talk nicely with one another. When it comes to intermixing TTL and CMOS, TTL will talk to CMOS, but CMOS will not talk to TTL. They will talk, as if you see in the previous picture, they will talk at the right voltage levels, but CMOS cannot drive enough current to drive TTL logic. So TTL requires a fair amount of current to turn on those transistors, whereas CMOS requires a lot less. So CMOS can't really drive the current that TTL requires. So if you're going to connect CMOS up to TTL, you probably want to put a buffer between them to enable the buffer to drive the adequate current that TTL requires. So like the name suggests, it's digital logic. So because the name logic there sort of implies that we're doing logical functions. So therefore there exists a series of gates to provide the basic logical functions. Of course, the most primary of any logical functions are the OR and the AND functions. So we have a gate to provide the OR function. The OR function, of course, when any of the inputs is 1, the output is 1 also. Of course, if both inputs are 1, then the output is 1 as well. So on the slide I show you the symbol that we use to represent the OR gate, a test circuit with A and B as the inputs and C as the output. I've shown you a timing diagram to show the relationship between the inputs and the outputs, and also a truth table here to show you how the output relates to the inputs. And of course the Boolean expression on the bottom to show how we might represent the OR gate in a logical Boolean expression. So in a Boolean expression, the OR gate is simply represented by the plus operator. The AND gate is the next logical function that we provide. We've got the AND symbol on the top left, a test circuit, the truth table corresponding to that test circuit. So you can see with the AND gate, when only both the inputs are 1, the output is 1 also. So when A and B are true, then of course the output is true also. And of course we have a timing diagram there to show you the relationship between the inputs and the outputs. Of course, ignoring any propagation delay there might be inside the gate. You can also see with the Boolean expression that the AND gate is represented by a dot. So A dot B is A and B. The XOR gate is the next logical function, next primary logical function, I guess. We've shown you the symbol on the top left, so it looks a bit like an OR gate, but it's got another line behind it. With the XOR gate, or the exclusive OR gate, this effectively works when only one of the inputs is 1, the output will be 1. So if both inputs are 0, then the output is 0. If one of the inputs is 1, the output will be 1. If both inputs are 1, the output will be 0. So it's exclusive OR. A, exclusive OR, B. So only one or the other. And of course, showing you a timing diagram again, and the Boolean expression. So the Boolean expression, when we use the XOR, it's a plus symbol with a circle around it. So it's a plus with a circle surrounding it to represent the XOR function. Okay, the next primary gate that we show you is the NOT gate. The NOT gate, of course, is useful for toggling or inverting the logical value. So effectively, if you put a 1 on the input of a NOT gate, you should get a 0 on the output. If you put a 0 on the input, then of course you'd get a 1 on the output as well. So it simply changes that input value to be the opposite. Okay, so test circuit here showing the input A and the output B. So you can see that the output is in fact the opposite of whatever the input was. And you can see in the timing diagram, simply the output just simply inverts. And of course, when you put in a Boolean expression, the NOT is represented by a bar across the input. So B equals A bar. Okay, so the next family of logical gates are effectively just a variation on our primary AND and OR gates. So these are our NAND and NOR gates. So these are ones which incorporate both the AND and a NOT, or the OR and a NOT. So we get our NAND, which is the AND plus the NOT, our NOR, which is the AND plus, our NOR, which is the OR plus the NOT, and effectively the symbols are the same as their primary gates. So a NOR gate is the same as an OR gate, but it has a bubble on the output. A NAND gate is the same as an AND gate, but it has a bubble on the output. And of course, because there's a bubble on the output, the Boolean expression is simply the same as a primary gate, which is, in case of a NAND gate, is A dot B, but then there's a bar across the whole lot to say that the whole output is negated. Same thing with the NOR gate. It's A plus B, and then the whole equation is simply knotted, so there's a bar across the A plus B. And of course, to show it in the truth table, it's exactly the same as the AND or the OR gate, but the output is simply the opposite. So with an AND gate, when both the inputs are 1, then the output is 0. In all other cases, it's 1. So it's simply the opposite to what we had with the AND gate. Same thing with the NOR gate. Situation where any of the inputs are 1, or both inputs are 1, then the output is 0. So only the situation where both inputs are 0, the output is 1. So it's simply the same as the OR gate, but with the output inverted. Of course, combinatorial logic is the statement that we use to represent a combination of all these gates to, I guess, implement some complex logical function. So even though we've got these primary gates, we can fuse these primary gates together to make quite a complex combinatorial logic function. So there is really no limit to what sort of logical functions we can do with these primary gates. One example of where these primary gates are used is in parity generation, and we'll talk about this in a bit more detail later on when we talk about serial subsystems, but parity generation is a very good use of XOR gates. So with our parity generation, effectively, in this case, it's an even parity generator. We effectively want to count up the number of 1s that we have in an 8-bit number, and then depending on the number of 1s, we either set the output to be a 1 or a 0, so that the total number of 1s in, say, a 9-bit word is effectively an even number of 1s. So when it comes to checking the parity, and this is where parity, I guess, is useful because it's a very simple error checking mechanism, is we might generate a parity for an 8-bit number, we ship it across long distances to some receiver down the track, which is obviously separated by some sort of distance. When we get down to that receiver, we generate the parity locally at that end, and then we can compare the two to make sure the parities are the same. If they're not, then we know an error took place. So at the other end, we simply pump it straight through the same sort of series of XOR gates to get a parity, and then we simply XOR the parity check with the parity bit that was in that, coupled with that 8-bit number that was sent down the line. And if the two are the same, then of course we get 0, which means the data is okay. If we get 1, then we mean that we've got some errors along the way, so we have to fix them up. So parity check is a common mechanism. It's a very good way of, a very simple way of showing the use of combinatorial logic to achieve some useful applications. The next sort of logical building blocks, so to speak, are our decoders and encoders. These are useful for converting, I guess, a binary number to, I guess, a particular output. So it's effectively able to use a switch, so to speak, where we can put a binary number into the switch and then have the corresponding output go high. So it's simply a binary to a particular output number converter. So I've shown here the two symbols for the decoder and the encoder, and I've also shown the truth table. So with respect to the decoder, when you have when A and B is 0, then of course the output is Z0 is high. If you put 1, 1 on AB, then of course the output Z3 is high. So it's effectively that binary number represented by AB, effectively the output corresponding. So AB, first one it's 0, then it's 1, then it's 2, then it's 3 in the AB column. And you can see that the output Z0, Z1, Z2 and Z3 go high depending on the binary number on A and B. So of course the encoder is quite the opposite. We can then use that to take a particular input that might be high. We can get it to generate the equivalent binary number that represents that input. Okay, so decoders and encoders are a very useful way of, I guess, if you've got, I guess, a lot of digital lines that you need to only have one line high at a particular time to, say, do some strobing sort of mechanism, you can simply pump a binary number to the decoder and it will simply make one particular line go high at a particular time. So it's very good for strobing or for if you've got multiple, I guess, signal lines that have logical high and you've only got a minimum number of inputs into your microprocessor, then you can use an encoder to encode the particular line that went high and encode it into, say, a smaller, code it into a binary number that then represents which line actually went high. So decoders and encoders are very useful mechanisms in microprocessors. Multiplexers are simply similar to the encoders and decoders, but they sort of take it to a higher level. With a multiplexer, it's effectively a digital switch where you have multiple inputs, and you can effectively, by changing the value on the S1 and S0, simply generate a pathway for that particular input to go to the output. So you can have, I guess, a switching mechanism where, in this case here, you've got 4 inputs, and at one point in time you can simply switch one of those inputs through to Z. So this is useful, I guess, in a way where you might have multiple devices and you've only got a limited number of I/O lines to connect to those various devices. So instead of having all those devices directly connected to your microprocessor, you might only have, say, 8 bits connected to a multiplexer, and then using that multiplexer you may then connect a various 8-bit device to the multiplexer at one point in time. So you can effectively switch between, a whole heap of different devices. So you don't need to have enough I/O lines to support all the devices. You can simply run through a multiplexer and have a multiplexer simply switch through those devices for you. I've shown the equivalent logic circuit there, which is a combinatorial logic circuit, and you can see that if you look at the truth table down the bottom, effectively when these input values of S1 and S0, you can see that it actually switches the D0 lines through to Z, depending on which value of S1 and S0 that you give it. Demultiplexers are pretty much the opposite. You can simply have one input going into the multiplexer, and then you can fan that one input out to various destinations. So we can effectively use, by the combination of a multiplexer and demultiplexer, you can effectively share one common bus amongst many different devices. Okay, so depending on which value of S1 and S0 you give it, you can effectively switch that bus, so to speak, through to a particular device. And I've shown you the equivalent logic circuit as well as the truth table for that device. So flip-flops and registers are a very important component in digital logic because our flip-flops effectively are our memory elements. These are basically logical circuits that remember. Okay, and the most simplest flip-flop that we have is the RS latch. So the RS latch is in 2 forms. You can make it from NOR gates or you can make it from NAND gates, but either way they effectively work in the same way. You can see if you make it from NOR gates, the R and S inputs are simply R and S. If you make it from NAND gates, then the R and S inputs are actually negated. So you've just got to keep that in mind. Depending on which way you implement it, out of NOR gates or NAND gates, then effectively the S and R inputs will change. So the beauty of the RS latch is that it's actually a circuit that has memory. So when you put the S line high, which is the set line, when you put it high, then effectively Q goes high. So you can see in the timing diagram when S goes high, Q goes high also. And when S goes low, Q stays high. And Q continues to stay high until our R goes high. Once R goes high, then of course Q goes low. So between S going high and R going high, Q has in fact remembered that value. Okay, and of course Q bar is the opposite. So it's a negated version. Depending on whether you need A or A bar, you can connect to the various Q or Q bar lines. So that's the basic way that RS latches work. They remember things, and they're great because that's how registers or memory works, is it remembers things. But of course RS latch is a very simple latch. You need to sort of take that to a few levels higher. So with the gated latches, you can effectively put on there an enable line. So therefore, if you say want to have numerous latches and you only want to be able to use one particular latch at a time, you need to be able to enable a particular latch at one point in time. So we have gated latches. So in this case here, we've taken our RS latch and we've connected the S and R through an AND gate to an enable line. So only when the enable line is high will the set and reset actually pass through to the RS latch. So with our enable gated latch, we effectively, with the symbol, simply an SR latch as before, but we have an enable pin on it as well, okay, which is simply just connects to those AND gates. So look down at the truth table, you can see that as long as the enable is set, set and reset happen normally. When the enable isn't set, then of course nothing happens, no change. So of course the RS latch doesn't actually change in any way unless of course the enable line is high. A D flip-flop is the other form that we can have. So with our D flip-flop, this is effectively our data flip-flop. We can simply put a value into it. So when we put a value high in there, then S goes high, R goes low. If you put a 0 into it, then of course S goes high, R goes low. Okay, because then Q will effectively mimic whatever that data line is. And of course, if it's not enabled, then the value doesn't change. So you simply enable the D flip-flop, and then you put the particular value in on the data line, and then it's reflected onto Q. So if you put a 1 in there with enable set high, then Q will go high. If you turn enable off, and you can put anything on the data line, whatever you want, it will not change Q. If you turn the enable line high and you put 0 on the data line, then of course Q will become 0. So effectively it's a good way of just having a single memory element, so to speak. And of course if you've got a whole heap of D flip-flops and say put 8 of them in parallel, then of course all of a sudden you've got an 8-bit register or an 8-bit memory element that can contain an 8-bit binary number. And of course I've shown this in a timing diagram as well, so you can see when the enable line's high, you can do whatever you want with data, and it's reflected on Q. Once you turn the enable line off, then of course whatever happens with the data line isn't actually reflected. So here it is shown pictorially. A JK flip-flop is another commonly used flip-flop that we use in digital circuitry. It's a great little flip-flop. So we have effectively has our SR flip-flop. We have these 3 input AND gates, and we have basically our clock edge detector circuit of our clock going into the AND gates. We have a J and K going to the AND gates, and we also have a secondary feedback path going from Q back into the AND gates. Okay, so you can see that when our clock goes high and J and K are both 0, there's no change. When our clock goes high and our J is 1 and our K is 0, then Q is 1. When our clock goes high and J is low and K is high, then Q goes low. And of course, if both J and K are high, then of course the output toggles from high to low to high to low whenever the clock is on the rising edge. So this is edge level detected. And I've shown down here the symbols for the JK flip-flop. So the top one's the basic symbol for the JK flip-flop. So you've got J, K, and you've got the clock. And the little arrow greater than symbol next to the clock line means it's positive edge triggered. And you can see the symbols down below that show the positive edge triggered. And if it's negative edge triggered, then it's simply a bubble on that symbol. So you can see this pictorially in the timing diagram. When our clock goes high, on the rising edge of the clock is when Q and Q bar actually change. So you can see when J and K are high, both high, and we simply toggle our clock. Every time the clock line goes high, the value of Q and Q bar toggles from high to low, and so forth. So it simply toggles that output. And that is a very important feature of the JK flip-flop, the fact that you can toggle it. And you can make a T flip-flop out of that simply by fusing the J and K lines together. And of course, if you fuse the J and K lines together, then we get a wonderful little feature which is useful for counters. So counters are a great little circuit, and we use them extensively inside microprocessors. Counters are used to keep track of the next instruction to run. Counters are used to keep track of, stack pointers. Counters are used to simply increment variables and keep track of variables and things like that. So counters are great little logical functions that we use in microprocessors a lot. So with a 4-bit counter, so if we had a 4-bit counter, simply we start with 4 zeros, and we can go all the way up to 4 ones. So I've shown here the process of the 4-bit counter going all the way from 0 all the way up to 15. So 0, 1, 2, 3, all in binary. Okay, so this is the format that the timer or the counter actually has to go through. And you can see that on the timing diagram, it's simply the least significant bit toggles up and down, 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 up and down. The next bit next to it toggles up and down, but it's at half the rate. So you can sort of see that if we pump the clock into a T flip-flop on the first one, we'd simply have it toggle up and down. If we took that output of that T flip-flop and pumped it into a next one, we simply get a divide by 2. And then, of course, you can see the one underneath that is simply a divide by 2 of the one before. So with each bit, the frequency of the oscillation of the output, I guess, the frequency of the output signal actually decreases by 2. So each one is a power of 2 less, so to speak. So we've got a divide by 2, then that's a divide by 2 of that one, which is effectively a divide by 4 of the original clock frequency, and that one is a divide by 2 of that one, which is effectively a divide by 8 of the original clock frequency, and so forth. So each time it's a additional divide by 2. So the way that we can do that with a counter is we can simply make a T flip-flop out of the JK by simply tying the J and the K together and simply making it positive edge triggered. Simply run a clock signal into there, and of course if we make our least significant bit that clock signal itself, and we simply put I guess a test point on the output of Q, we can see that A toggles up and down and B toggles at half that frequency. So if we start from the right hand side, we can see that we have A is 0, 1. So it's A is 1, B is 0, so that's 0, 1, which is 1 in binary. And then we have B is 1, A is 0, so that's 2 in binary. And we have B is 1, A is 1, which is 3 in binary. And then, of course, it toggles back to 0 again. So then we start back at 0 again. And then we go 0, 1, which is 1, 1, 0, which is 2, 1, 1, which is 3. So it simply counts up 0, 1, 2, 3. And then it rolls over 0, 1, 2, 3. Rolls over 0, 1, 2, 3. Okay, so counters are a very good way of incrementing variables. So we simply have a JK flip-flop, and every time we pulse it with a clock, it simply increments. When it comes to describing these logical circuits in the real world, so to speak, we don't effectively draw schematics. I mean, I guess you can if it's a very simple logic circuit that you need to do, then of course you can draw it in a schematic and make all the AND and NOT gates and wire them all together. But when it comes to very complex digital circuitry, we effectively use these predefined languages, which are hardware descriptive or hardware definition language or hardware descriptive languages, such as VHDL or Verilog. These languages allow us to describe digital circuits in a very, I guess, abstract sort of level, a bit like how we can describe our code using a C language. We can effectively also use a high-level language like Verilog or VHDL to describe a digital circuit. So should you require any further assistance, then please do not hesitate to ask your demonstrator, post a question on the forum, email me, the convener, or make an appointment to see me. Either way, please ensure that all your questions are answered.